Hello and good day everyone. Today we are from Team 4 and we will be presenting on our team mini project. So this team consists of me myself, Sharvin Nagamuthu, Muhammad Fariduddin, Ho Zijun and Daniel Haikal Fikri. So to begin the calculations, we first have to look at extraction column 2. A basis of 7.5 kilomole of glycerin per hour is given by the question at stream 20. And also at stream 18, the molar composition of ACP and PMC are given as 0.6 and 0.4 respectively. So, by using this information, we can then obtain the values of N34, and by using the information 93% of extraction efficiency of PMC, we can obtain the equation below. By performing ACP balance, PMC balance, total balance, and glycerin balance, we will then be able to obtain the values of N32, N31, Y1, and Y2 respectively. Moving on to the heater 3 unit, the molar flow rate entering heater 3 unit is equal to the molar flow rate exiting the unit. Therefore, M21 is equal to M22. And moving on to distillation column 2, we have 4 unknowns to be found here, which are N33, N34, N35, and N36. And an information of 86% of PMC of feed removed is given by the question itself. So by using this information, we can obtain the value of N33, which is 3.11, and by performing ACP balance, glycerin balance, and PMC balance, we will be able to obtain the values of N34, N36, and N35 respectively.
Next, we move on to distillation column. First of all, we write the known value, which is N31, that we get from the previous apparatus. Then, from questions, we can get that the mass fractions of stream 16. We convert the mass fractions to mole fraction by assumed base is 100 gram. After we get the mole fractions of stream 16, we can do our calculations by using EB, PMC, ACP, mass balance. After we get all the mole flow rates of every stream, we can calculate the mass flow rate at every stream. For heater 2, as the stream 15 and stream 16 is same, thus we can conclude also that the mass flow rate of stream 15 is equal to mass flow rate of stream 16. Next, we move on to extraction column 1. First of all, we write the known values. Then, we do for the DOF, and the DOF is not equal to 0, which means that we can't solve it first.
For flash separator, for stream A, there are 4 known and 4 unknown. For the known, we can get the value from condenser part, and for the unknown, we can get the value by using EB balance, ACP balance, PMC balance, and BA balance. For stream 9, there are 0 known and 3 unknown. For the unknown, we can get the value by using O2 balance, N2 balance, and CO2 balance. For stream 10, there are 4 known and 1 unknown. For the known, we can get the value from neutralization reactor, and for unknown, we can get the value by using H2O balance. For neutralization reactor, for stream 10, we can get all the value from flash separator. For stream 11, the only unknown is N.22. We can get the value by using the information given, which is by dividing the molar flow rate for NaOH to its molar fraction. For stream 12, there are 3 known and 2 unknown. The 3 known, we can get the value from extraction column 1. For the unknown, we can get the value by using extent of reaction.
Next is mixer. From mixer, we can find N1 from ethyl benzene balance, and then we can also find M1 and M2. Next is heater 1. From heater 1, we know that M2 is equals to M3, which is equals to 1843.9 kg per hour. And then pump, for pump is also the same, in equals to out, so M3 equals to M4. So M4 equals to 1843.9 kg per hour. And then for compressor, M5 is equals to N5 time with average molecular weight. And M6 is equals to M5, which is equals to 13760.91 kg per hour air. Next, we move on to oxidative reactor. For the oxidative reactor, first we list all the equations. First is main reaction, and then side reaction 1, and also side reaction 2. Then we find extent of reaction 1, extent of reaction 2, and also extent of reaction 3. From this, we can find all the unknowns. When we got all the unknowns, we times with average molecular weight, which is equals to 31.7. Then we can get M7, which is equals to 15604.85 kg per hour. Okay, next is condenser. For condenser, M7 is equals to M8. Next is energy balance problem. So this is our table of information. Our reference state is the same for every unit process, and our assumption is, as the pressure difference between each streams are small, effects of pressure are neglected. Next, we have to find enthalpy for every stream. The enthalpy for every stream is basically using the same method, either using delta HF, CPDT formula, or interpolation from table B8. So I just go through it. So for total enthalpy for stream 1 is negative 50.22 kilowatt. For stream 2 is negative 62.9 kilowatt. For stream 3 is negative 27.98 kilowatt. For stream 4 is equals to stream 3, negative 27.98 kilowatt. For stream 5, the pressure difference is too low, which is 180 m to 1 bar, so we can neglect it. So H1 equals to 0. So total enthalpy for stream 5 and stream 6 is equals to 0. For stream 7, we use several methods because stream 7 consists of a lot of compound. So the first method we use table B8, interpolation from table B8. We can find H1, H2, H3, and then H4B, we use CPDT formula. Then we get H7 and also H8. And then the question asks for the power in this reactor. So we list the formula first, and then we assume delta EP equals 0 because no change in elevation, delta AK equals 0 because no change in velocity, and W equals 0 because no moving parts. And then we can get Q equals to negative 1759.4 kilowatt, which is power released from the reactor. For table B8 is also the same. We use interpolation from table B8. This is using CPDT formula. Okay, this one is interesting. As you can see here, to find H6C, we must use Watson correlation. We can get the value of H6C, which is equal to negative 89.26 kilojoule per mole. And then for H7B, we assume, by referring to the Perry Chemical Engineering Handbook, we assume the standard heat of benzoic acid formation R equals to infinity. So we can get H7B equals to negative 27.2. Then we find H7C and we get H7. So we find H8. And then the equation asks for the power. So we use the same formula as just now. And we get the power equals to negative 762.14 kilowatt power release from the reactor. And then the equation also asks temperature which the TDP, the temperature which the elements start to condense. So we find the mole of H2O, and then using Rod's law we find TDP, and then we can find TDP from interpolation from table B3.
For flash separator, this is the hypopath for O2 gas. The answer for H1 is 1.643 kJ per mole. This is the hypopath for N2 gas. The answer for H2 is 1.606 kg per mole. This is the hypopath for CO2 gas. The answer for H3 is equal to negative 391 kJ per mole. For the total enthalpy of stream 9, the answer is negative 3 to 1.68 kilowatts. For stream 10, this is the hypopath for EB liquid. The answer for H1 is negative 2.06 kJ per mole. This is the hypopath for ACP liquid. The answer for H2 is negative 130.36. This is the hypopath for PMC liquid. The answer for H3 is negative 206.38. This is the hypopath for BA aqueous. The answer for H4 is negative 407.85. This is the hypopath for H2O liquid. The answer for H5 is negative 281.693. The total enthalpy stream at stream 10 is negative 2180.89 kilowatt. For neutralization reactor, for stream 11, this is the hypopath for NaOH aqueous, and the answer for H1 is negative 435.26. The total enthalpy at stream 11 is negative 638.11 kilowatt.
Next, we will calculate the enthalpy of every stream involved in the extraction column. First of all, we draw a table. Then, we draw the hypothetical path for every substances in stream 12. We're solving this hypothetical path by using heat of formations method. So first of all, by using the heat of formations liquid, we can form EB in liquid at 25 degrees Celsius. Then to get the desired 80 degrees Celsius, we need to use CP to calculate the enthalpy. We can integrate the CP and do the calculations. Since the change of pressure is very small, thus we make assumptions that the change of pressure are neglected in every calculations. Then by adding H1A, H1B, and H1C, we can get the enthalpy 1. It goes same to the other substances. For PMC, we're specially using Watson correlation. It is because we need to get the desired pressure at 80 degrees Celsius for PMC liquid. However, we doesn't have the CP liquid for PMC. The desired SB is in aqueous form 80 degrees Celsius and 2 bar. Since we only have the heat of formation of SB in solid, so we use the heat of formations of SB in solid. Then, to make it into aqueous, we add it with the heat of solution. Due to the lack of informations, we assume that the heat of solution of SB is equals to 0. Then, the SB aqueous from 25 degrees Celsius is increases to 80 degrees Celsius. For this enthalpy, we assume that the heat of capacity of these solutions is the heat capacity of pure water. Thus, we use the CP waters to do the calculation. After calculates all the enthalpy of every substances, we find the total enthalpy for every stream. It goes seems to stream 13, 14, and also 15. In question 6, we are required to calculate the heat release or heat absorbed by the extraction column 1. First of all, we write the energy balance equations. We do assumptions that the EP is equal to 0 as no change in elevation. We also do the assumption that the EK is equal to 0 as no change in velocity. We also assume that the work shaft is equal to 0 as no moving parts. Thus, our Q is equal to the change of the enthalpy. This, we can get that the Q is actually equal to 0 kW, which means that neither heat release nor heat absorbed. It goes seems to the heater 2. We draw a table and draw the hypothetical path. Next, we move on to the distillation column 1. We also use the same method. For question 8, the questions are requires us to find the power needed by the distillation column 1. First of all, we write the energy balance equations, then we do the assumptions, and what we get is just Q is equal to the change of the enthalpy. And finally, we can calculate the Q is equal to 29.49 kW.
At extraction column 2, you have to find the total enthalpy at stream 21. So firstly, you have to draw the hyperpath for ACP from 25 degrees Celsius to 150 degrees Celsius. And HA1 can be obtained from the information table in the Excel file. H1B, however, can be obtained by integrating the heat capacity of ACP from 25 degrees Celsius to 150 degrees Celsius. And H1C can be neglected because the change in the pressure from 1 atm to 2 bar is the slightest. So therefore, we will be able to obtain the value of H1. And next, for PMC, we also have to draw a hyperpath from 25 degrees Celsius to 150 degrees Celsius. H2A can be obtained from the information table in the Excel file. H2B can be obtained by integrating the heat capacity of PMC from 25 degrees Celsius to 150 degrees Celsius. And H2C can be obtained by Watson correlation. And for H2T, it can be neglected because the pressure change is slight. Therefore, we can obtain the value of H2. And for glycerin, the steps are followed similarly to ACP. Therefore, we can obtain the value of H3. And through energy balance, and by neglecting the change in elevation, change in velocity, and the work done, we are able to obtain the equation Q equals to delta H. Therefore, the answer will be 39.11. At heater 3, we have to find the total enthalpy of stream 22. As you can observe here, the steps are similar to the extraction column 2. But however, for H1B, we have to now integrate it from 25 degrees Celsius to 220 degrees Celsius. And same goes for the PMC. However, by using Watson correlation, we now obtain a different value for H2C, and the same steps are implemented for glycerin. The only difference is that now that the temperature increases from 25 degrees Celsius to 220 degrees Celsius, and therefore we can obtain the value of H3. And the total enthalpy of stream 22 is negative 1150.68 kilowatt. Now, for distillation column 2, we have to find the total enthalpies at stream 23 and 24. Again, we have to draw the hyperpath for ACP, but this time it's in gaseous state. Therefore, the value of H1 can be obtained from the information table in the Excel file, and the value of H1B can be obtained by integrating the heat capacity of ACP in the gaseous state from 25 degrees Celsius to 220 degrees Celsius. And again, HC can be neglected. Therefore, we can obtain H1. And for H2, we have to draw the hyperpath for PMC in gaseous state only. Therefore, we can obtain the value of H2A from the information table, value of H2B from integration, and the value of HC again can be neglected. Therefore, the total enthalpy of the stream 22 is negative 83.25 kilowatt. Now moving on to stream 24, we have to draw the hyperpath for PMC as similar to in the heater 3. Therefore, the values are all the same as heater 3. And for the glycerin, it's exactly the same step as in the heater 2. So therefore, we can obtain the value of total enthalpy at stream 24, which is negative 1348.66 kilowatt. And by carrying out energy balance, we can obtain the value of Q as 68.77 kilowatt. That's all from us. Thank you.